Still talking about moments of inertia. It's important to remember that moments of inertia are additive. And what do I mean by that? Well, simply, if I have a moment of inertia by particle 1, particle 2, particle I, particle n, we just add the moments of inertia. So total moment of inertia will be simply be I1, the moment of inertia of particle 1, plus the moment of inertia of particle 2, plus the moment of inertia of the ith particle, dot, 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 plus the moment of inertia of the nth particle. And of course, for point particles, we can write it in the fashion shown here. Now, let's talk about the integral formulation for this concept. We show here an extended rigid body and a mass element drawn here in the picture. We'll call that mass element dm. Now, we also have the distance from the axis r, where the dot is the axis of rotation. So I can write that the contribution to the moment of inertia, di, is equal to the element dm times r squared, the distance, where r is the distance from the axis of rotation. So the question becomes, how do I sum up all the elements to get the total moment of inertia? Well, I need to integrate, and I'll integrate r squared dm over the complete volume of this particular extended rigid object. Now to do that, I have to know what? I've got to know m as a function of r. If I don't know m as a function of r, then I'm going to have difficulty. Or we have to cast m as a function of r. Now, what I'd like to do is start by considering a rod rotating about an axis. And I show the axis over on the left hand side, and the rod is length L. Now I can take a small element, dm, but that's related to dx, and we're going to consider that the rod is uniform, has a uniform mass per unit length. And I ask the question, how is dm related to dx? Well, dm, the mass contained in that little element x, will be equal to the mass per unit length times dx. Now, let's just pause the video just a minute and think that through. Make sure you convince yourself that what I'm saying there is correct. Now let's integrate to get the complete moment of inertia. So if I form the integral from x squared dm, it'll be mass per unit length, integral from 0 to L, x squared dx. And we come out with 1/3 ml squared. And it would be to your best interest to perform the calculation yourself and convince yourself that it is indeed 1/3 ml squared.